started, let me get this over to the right screen here, make sure that we are running the latest version. I was trying to come up with a better way of explaining the loops one and realizing it was turning into a bit of a mess, so I was just like, we'll talk it through a little bit, but just be aware, that is why you would need to read an entire one of these books. The matter of loops is where all of the complication comes in, and it is kind of an interesting subject all into itself. But we'll get to that in a second. Anyways, then is it F5? It is. All right. Welcome to the August Formal Methods User Group.
We're talking about healthcare instead of.
We started, let's talk about healthcare. Exactly. Yeah. Right. Before we get started, we've got to thank Capital Factory for giving us this awesome space. It has been a pretty nice location and everything, and so we definitely appreciate the assist there. If anybody's interested in membership, we've got a QR code here that will let them know that you found it through us, I believe. And so definitely, if that is something you're interested in, just let us know and get you hooked up with folks. It's a pretty good spot. Also, we've got a Zulip. It is kind of a invite only, so if you're interested in the Zulip, just let us know. We've got a couple people who are admins on it, so we can get you hooked up in there. We have occasional chat about different topics related to this stuff, and so it's not super high volume at the moment, but there is an amount of discussions that happen in there, so definitely let us know if it's something that you would be interested in. And as a reminder, the definition of formal methods that we have been operating under is that formal methods are techniques and tools which use rigorous mathematical logic to design, analyze, and verify systems with provable properties like correctness, reliability, and security. So, tonight's topic is correctness by construction using the weakest precondition predicate transformer. It's a topic that is very interesting to me in particular. That's how I got into formal methods. But it is also a very deep topic. It's probably, in some ways, the lowest entry into this topic is a little bit more challenging than the lowest entry into our previous topics. But it is still not so deep. Like definitely the deep end of the SAT solver and SMT solver is every bit as deep as this, or possibly deeper. But the entry level to this one is a little bit higher in order to really start using this for something. And so if anybody is interested in this, we'd love to get you started on it. I think it's probably approachable to everybody in this room, but it is something that if you get stuck, let me know, I can help out. So for me, all this formal method stuff began when I was in undergrad at East Central University in Ada. So on our last week of the compiler design class back in December of 2009, I heard bits and pieces about formal methods before. I think it's somewhat unusual. They don't usually talk about that in undergraduate departments. Occasionally you'll find a university with a particularly strong graduate department doing formal methods where the topic might come up, but it is unusual. And so we were very odd that we didn't even have a graduate department, yet we were at least mentioning it. But on the last week of the compiler design class, we finished early, and so the head of the computer science department, Dr. Bill Walker, this was one of his last classes before he retired, so he decided he was going to spend an entire week just talking about formal method stuff because he thought it was interesting. And we didn't go very deep into anything. We just kind of surface level discussions about what are different things that are in that topic, in case there was anything that really jumped out at folks. It was interesting, but I wasn't really sure what to make of it yet. It was largely new, kind of a different area that I dealt with in undergrad computer science, or even computer science and math double major. It wasn't super familiar with all of this stuff, but it was interesting, and he recommended this book at the end of it. And so I went and got a copy. This is not the original copy I got, but this is just another one I got. And then a few months later, during a snowstorm, campus got closed down for a couple days. I was stuck in my dorm, nothing to do. It was too early in the semester for any like real homework assignments or anything. So, okay, well I'll just sit around and read this book that I got, you know, put it on the shelf because right before the holidays, I decided to pick it up. And to be honest, at the beginning, it was a little bit frustrating because I was a computer science and math double major, and this particular book starts off where he's trying to explain the basics of set theory using this bizarre notation. I think he wrote this book in Trough instead of, because like LaTeX, tech existed I think by the point he wrote this book, but it was still very new, and LaTeX I don't think even existed by the time this book was written. And so all of the symbols that he made, math symbols, were just bizarre. They don't make any sense. Like, they're difficult to read because it's just like, what? A big capital E means there exists, and a big capital A means for all, and it was just like, as a math major, it bothered me because I knew that tech and LaTeX existed, and I'm like, why is this?
And the alternate method using Trough doesn't allow for the special characters?
Well, this is before Unicode, before UTF-8 for sure, and probably before Unicode was even finalized in its earlier forms. So like, Trough might have been able to do that with Unicode and everything, but that wouldn't have been baked into the symbols that the printers would have had. Certainly, when he started this book, I don't think printers would have had like math symbols and stuff on ready hand, unless you went to like kind of a specialty publisher. In fairness, he went with Springer, so presumably Springer had a copy of the math symbols, but whatever.
Which what was the year?
What?
What was the year of the book was written or published?
So first publication was 81.
Wow.
So that presumably that means that he had been working on it for a few years before that. It was like that book, the Dijkstra's, was 76, and in a sense, this book is kind of an attempt to make that book, the very short book, comprehensible to anybody who was not like a world-class computer scientist, because the consensus apparently was at the time, like that was groundbreaking. Dijkstra's, you know, a discipline of programming was this groundbreaking work, and that like no PhD student had the first clue about what the hell they were talking about in that book, and a not insignificant number of professors maybe had no idea what the hell he was talking about in that book, because it was a little bit, he hit the ground sprinting in that, which is why it's so thin. It's such a small book, but David Grease took it on himself to make a version of this material because he felt that an undergrad CS student might just barely be able to understand it as long as it was explained in terminology they could appreciate. And so while the symbols threw me at first, once I actually got to the meat of this book, it was the first technical book I could never put down. Like, I got into the section 2 where he was justifying kind of like the concept of correct by construction, just the kind of general approach and everything. And I was hooked. I got through the whole book in about 48 hours or so. I didn't sleep a whole lot. I did most of the homework problems in there. It was fascinating. So I told Dr. Bill Walker about this, that I was like, okay, that book you recommended, I devoured it over the course of like last week. You know, is there more stuff that I should look into? And he gave me a bunch of other resources and stuff. But one of the things was his wife, Dr. Anita Walker, who was the head of the math department, heard that I got into this, and she recommended that I consider using the techniques described in this book do a math research paper, because that's a requirement to get a math degree, and I was pretty, I was gonna be finishing my computer science degree that semester, but she knew that I was also really close to a math degree, and so suggested that I consider that. And so, yeah, that next year after I finished my computer science degree, I stuck around for another year thinking I was gonna finish my math degree. That's another story for another day. I didn't, but that's, turns out I finished all my math prereqs, but I didn't have enough gen ed electives in order to get a second degree. I didn't know that until years later, though. Like I was recruited to go into the tech industry before I got a chance to finish those. So, anyways, for my math research paper, I did program derivation of matrix operations and time-ordered finite fields. And the matrix operations were easy, but the thing that was I got stuck on for a while was I wasn't very happy with my proof about multiplicative inverses. And so I wasn't originally just going to do finite fields of prime order. I was going to do finite fields of prime power order, because the idea was in the previous semester I had done a class on proof-based cryptography and was surprised at just how many people who were doing this proof-based cryptography stuff were using these like libraries written in Python or like C or whatever that had no proofs. Like I was doing proof-based cryptography, and then like all of the actual like things people were using in production were broken as hell, full of bugs, and I'm like, how is it that we're okay with having like all these cryptographic libraries that are just utter garbage? Like, how is it that we're okay with this? And it turns out that there are some people who are not okay with this, but also this is not the kind of thing that one dude in an undergrad was going to make any kind of dent in. I wasn't so delusional that I thought I would, but I thought it would be a good exercise to start playing around with. And it turns out that the one thing that was bothering me was my multiplicative inverse part. And from playing around with the weakest precondition, I found an algorithm that I had never seen before that did multiplicative inverses with, basically modulo primes is basically what it is going to be in particular. And it's the most efficient possible one you can have. I mean, like Big O, you couldn't have a faster one without it breaking a bunch of complexity rules about the nature of numbers. And so I knew that was equivalent to the fastest possible algorithm to come up with for that. Now the algorithm didn't work at all for prime powers, and it didn't work at all for other kinds of scenarios. So maybe not the most useful algorithm ever, but it was still cool. It was something I had never seen before, and it popped out of using this techniques that we're talking about. So that was how I got introduced to this stuff. So now, okay, I haven't even said what the hell we're actually talking about yet. So, well, first of all, let's have a reminder. How is software usually created? Well, right now, you're like, hey, we got a program. And it's like, you're just like, type. We're gonna write a program, not thinking about it, just write some shit down. Yeah, what's up?
Wait, so my professor actually told me that, like, back at the university, right? That, like, first you write the spec, only then you write the code. So,
Well,
like,
okay.
before you write the function, you write the contract for the function.
We'll get to that next.
Okay.
We're just gonna say for now that most software is written by type. We got some code.
That's what I told
Now-
him, and he told me
now
no,
we're gonna
that's
do-
not how it's written.
Most code is written that way. Yeah. And maybe like best practices, what would be called quote unquote best practices, would be as if you swap order 1 and 2. Like if you do test-driven development, you write your unit test first, and then you write the code that implements the unit
Well,
test.
now it would be log into ChatGPT, give it a prompt for what kind of code
Yes.
I want to write.
Yeah, you
I
start.
would argue that a lot of the code that's written in business, that there's no formal test. There's like a few test cases the person remembers and types in, and they always forget 1 or 2, and then that's where it goes.
Yeah,
That's
essentially.
Java development plus copy and pasting from Stack Exchange.
Yep, exactly. And so that's how most software is written today. But there is an alternative. So you could develop software using what is called the correct by construction approach. And in this particular example, I'm going to describe weakest precondition. We'll get to that in a second. So you specify what is the desired outcome of your program. That's what you start with. And then after you say what is the desired outcome of your program in like a mathematical sense, you're going to be using all these like predicates and stuff that we've been talking about for in several of our different talks. After that, you repeatedly derive, automatically calculate, what is the code that would have been run to get us that outcome. So you know what it is you want to achieve, and then you keep taking one step back at a time to figure out what was the code that got us there. And you keep doing that until what comes out is the preconditions, the situation that you would start with that matches the reality of what is the environment in which your program will run. So you just keep doing that, keep doing it until you get to
Sorry, just a burning question, but feel free to defer because it's
Yeah.
totally mine. Isn't like specifying the desired outcome like just as complex as like what the code is actually?
That's actually my question.
Wait, isn't it like-
Because we were just talking about agile,
Agile.
that's the whole logic of agile, right? The claim of agile is that the complexity is not in the program, it's in the understanding the desired outcome.
So you correctly represented what.
Yeah, which people are way fickle in.
Wait, so isn't what you described, isn't that like the test-driven development, basically?
You could, in this case, I'm talking about doing it in a formal sense.
Yeah,
Right.
yeah.
So, yes, but.
So we're in a vacuum in which we have a like simple desired final outcome.
Yeah, this in a certain sense is the extreme end of test-driven development.
Every
where-
single case is tested.
Yeah,
Well,
yeah.
correct myself, like, you'd split the difference like test-driven development, and you'd specify like 4 cases that would cleanly like shatter the space of possible outcomes.
Yeah.
And then that would only be a few cases, and. yeah.
And that's the trick here is we'll show it here in a second. In a sense, our test, if you will, the desired outcome that we're specifying, and then the sequence of derivation of the code that would get us there. The idea here is that we specify our desired outcome with a level of precision that makes it so that we don't have to write the code at all.
It's directly inferred algorithmically from the
Exactly.
specification.
So given the language, the programming language, you can actually extract. So that's another name for this. You've got correct by construction. Sometimes you call it program derivation. Sometimes you call it program extraction, synthesis. There's a bunch of different names for kind of the same idea. If you specify your outcome clearly enough, then you can actually derive what is the program that looks like that would give you that outcome. Yeah, now you can have infinitely many programs that will give you that outcome. What you're doing is you're extracting automatically one program that will only give you that outcome. That's it. That's the idea. Given a particular program.
So hold on, sorry. So you get a program, and that program can only express that outcome. Is that inherently the most efficient program that can do that outcome, or?
It's not necessarily. That has a little bit to do with the particulars of how how it's represented in that.
It is not inherently the most efficient program that can reach that
It
outcome.
tends to be.
Okay, tends to be.
It tends to be, yeah.
Okay.
But it's important, since we're talking about proofs and stuff in this case, it's important to point out that we don't know for sure that it is.
Okay.
And that may have to do with how the weakest precondition
So it just gives me
was.
a high probability of the most efficient program.
Yeah, it's a very good chance of it, it turns out. Knowing whether or not a particular algorithm is the most efficient is in general undecidable.
Yeah.
But depending on how you happen to implement
Cause my question was gonna be, if I don't know that it's the most efficient program, why then would I wanna do that, but if it's the most likely to be, then,
Yeah.
yeah, it makes sense.
The idea is, whether or not it's the most efficient, it is one that has no bugs with respect to the specification.
Okay, yeah.
And so that is usually what it's pitched as, it tends to be a very efficient implementation. People who want efficient implementations usually aren't going to be aren't gonna be willing to spend the cost on that level of specificity.
But it saves me the time on debugging versus the cost of, I'm running in the cloud or whatever on.
It does,
the most
but
efficient.
it's more often that it's the people who are willing to spend the time and money to do this, they're doing that because the cost of failure is so high that they won't even accept the possibility that it's wrong.
That makes sense, yeah.
And so things like an algorithm for checking some important details about a credit card out, like transaction or something like that, they will absolutely use weakest precondition.
I was gonna say healthcare, but the precision
Yes.
of outcome problematizes in healthcare because a lot of times we don't have that precision of outcome because biology is so.
Well,
Follow.
yeah, if we're talking about biological, outcomes, but healthcare isn't just biological measurement either. So one of the examples is going to be the software that runs a pacemaker. They're absolutely different.
Okay, yeah, cause that's
Yeah.
reducible mathematics.
Yeah, it's not saying that the conditions in which that pacemaker were.
But if I were trying to say do it like a pharma test on like a drug or like a cancer.
Yeah,
or
that's not
something,
something-
That's not reducible for the precision of outcome.
Yeah, exactly, that's right. Now, it could be if you're talking about the machines that make them, and so you wanna make sure that if you measure this thing on this machine, then you have to.
Yeah, cause that's mathematically reducible.
Yeah, exactly, and so if you're talking about a program that is doing a particular task.
Something where the outcome I'm fed, in between the outcome that I'm using to derive the program, before that is made the assumptions of quantification of the.
That's right.
Process.
Exactly,
Okay.
exactly. So there are some circumstances
So
related
I'm
to.
allowed to give the mathematical mapping as a assumption.
Yes, yeah, exactly. So it's not necessarily going to be applicable to some very high level thing.
But if I'm already accepting a quantification as an abstract, then it's usable.
Yes, exactly.
So something you mentioned, sorry, this is slightly a tangent. You mentioned that the asymptotic runtime of programs derived from this can be undecidable?
No, the determining whether or not a given program is the most efficient possible
Of all
implementation
possible
of that program.
Okay, so
is
just for
for arbitrary programs.
yeah, for a weird problem, but for most problems we
Yeah,
know
most problems
somewhat
we
what the best case is, and then you can say is it the same as the best case?
Yeah, so most programs we don't know, most programs you're going to run into, you will know. I'll put it that way.
Yeah.
So it's like in the scheme of all programs which could possibly exist, then no, we don't generally know.
Yeah.
On the flip side, in the same way that the vast majority of numbers are irrational in the reals, and yet we almost know truly irrational numbers that have nothing, non-algebraic, transcendental numbers. Almost all of the numbers on the number line are transcendental, and yet we know almost none of them.
Almost all of them are undefinable,
Yeah.
exactly.
Yeah.
And the very few
Not
that
even
we
something
have
below.
are all algebraically related to the handful that we do
Yeah.
know.
But it's an acceptable assumption given we have to make a decision at some point if this is a
Yeah.
real life program.
Yeah, exactly. So, yeah.
So is, in the specified desired outcome, is this, the same as high level programming languages where, specifying the desired language could be code in a high level programming language and then the repeatedly derived is the low level interpretation of the high level programming language?
That's
Kind
a
of
very
like
good
how
one.
Java, whatever, does a bunch of stuff underneath the covers to do its garbage collection for you. And so, in that case, you could give it inefficient specified desired outcomes.
That is an interesting line of discussion that is outside the scope of this.
Okay.
We are absolutely going to be talking about that line of thinking future, probably once we start to get to semantic definitions of languages. But not yet. But yes, you're right on a very important line of reasoning.
So to answer his question, for the purposes of this, are we assuming a low-level language or just a blanket abstract of any particular language?
We'll get to that too. So right now, I'm just describing the approach.
Okay.
So there are alternatives. So I say this correct by construction, and this, to be clear, the things I am saying here are the weakest precondition approach to the correct by construction using the weakest precondition. There are alternatives. So in this case, we are talking about you have a post condition that you have specified very clearly, and from that you are mechanically deriving the program that implements that. There are other ones. Instead of the weakest precondition, you have the strongest post condition. So you have a very clear definition of the initial state, and then you're using that to get to somewhere. That sounds like that's more logical, that clearer reasoning forward, but it can be difficult. Usually when we think of programs, we know where we're trying to go, and then figuring out how did we get there is, even though it sounds backwards, it's usually an easier thing for humans to figure out than the other way around, where you have a very clear idea of where you currently are, and then vague notions of keep going until what you wanted to achieve is a subset of where you're going. And so it takes a lot more cleverness in your choice about what's the next thing you put in the program. There are circumstances where it makes sense, but I think it's more, all of this, without getting into the details or whatever, basically you can think of that as just another concept, instead of starting with the strongest goal, starting with the destination and then working your way backwards, which is the easiest one usually to wrap your head around. There is an alternative. We're not going to go into a lot of details of that. There are people who study that. Perhaps more interesting and more practical, Leslie Lamport, several years after this, came up with two variants, the weakest invariant and the strongest invariant. He came up with those in both the same paper. And those are pretty interesting unto themselves. So you're trying to do this weakest precondition stuff, but for like ongoing running programs. And so that's really practical for a different reason. So if you're having like a PID controller and it's really important that that thing be correct, well, the way that the weakest precondition is framed, it doesn't map to that. And so the weakest invariant and the strongest invariant try to get you a similar setup to using the weakest precondition, but for circumstances that make more sense there. I don't think it was that big of a conceptual leap getting from weakest precondition once we get to loops, which we're going to hand wave past. But if you understand what you're doing with loops, these aren't such a big conceptual leap. But it was nice to have somebody point out where those definitions do actually diverge a little bit from the weakest precondition. But suffice to say, there are alternatives to just the weakest precondition, which you might use in some different circumstances. We usually go with the weakest precondition predicate transformer when we're talking about correct by construction. This idea that you have specified what you're trying to accomplish with such clarity that the entire program can just be generated from it. We usually use the weakest precondition, in part because that's kind of how the ideas were introduced, because that's where the majority of the papers that have been written are about it. Most of the people who implement something like this, if they have a programming language that they want to implement weakest precondition for, correct by construction for anything, they're probably going to do weakest precondition first, maybe only. So that's where we usually do it. And a lot of times you'll hear someone say weakest precondition. It's another one of those colloquial. Weakest precondition, in a sense, that is the thing that we're trying to get. Sometimes people use the term weakest precondition to refer to that program that does it, or the trick, or the particular tool, or sometimes they'll just use WP, which is not confusing at all given where I work. So yeah, you'll see all of these terms used interchangeably, unfortunately, and sometimes you'll have to like read it a second or third time and be like, okay, in this circumstance, do they mean a particular precondition, or do they mean the general approach, or do they mean the function that's determined based on the particular programming language? You may have to figure that out, unfortunately. So, next, let's get into the weakest precondition, and a particular example of it. So, you're going to see some notation that comes up a lot. When dealing with this kind of thing, you have this notation called the for triple. It's usually written something like this. Q, S, R is kind of common letters that you will see for it. Sometimes you'll see different letters. Basically, the idea is Q is the state of the entire computer or whatever before you run the program. S is the program that you're going to run. And then R is the state of the computer after you ran that program. Yeah, and so the precondition Q, that's the term we would use for that. It's just the circumstances before the thing runs. And then R is the post condition, and then S is just the program. So the weakest precondition, predicate transformer, which we'll write is the lowercase WP a lot of times. You usually write it something like this. So you have WP, S is the name of the program, R is the post condition you're trying to achieve. And then this Q, or Q prime, or whatever, I'm calling it Q prime here to make a point on the next slide, is the weakest precondition that you could start with, that after you execute S, you're going to get to state R. So that what had to have been true before you ran the program, so that after you ran the program, R is the case. And R is one of these like Boolean statements, like we've talked about in the past, like with the SAT solver talks, where it's just a bunch of things which we happen to know are true. We're not going to talk about how we know they're true. We're just going to say they're true magically. They're true. And
well, weakest precondition is the thing that most had to be true.
Yes. So the output of this thing is what had to be true in order for program S to get us into state R.
Well, sorry, I'm a little confused. So is it everything that had to be true, or you said the thing that weakest precondition thing that most had to be true?
Yeah. So we'll get to that. So
sorry.
yeah, no, you're good. You're good. So the observed precondition might not be the weakest one. So that's worth pointing out. So it could be that there are other things which are also true. There could be other things which are true about the state of the program.
And your previous notation was inclusive of those things that were true, but may not necessarily be most had.
Exactly. That for triple, it's not necessarily specified whether that is, the implication is that is everything that happens to be true. Yeah. And that R is everything that happens to be true afterwards.
Regardless of whether or not it's the weakest precondition.
Whether or not it's the weakest. The idea is this weakest precondition is it's only spitting out the thing that has to be true. So maybe there's other things which are also true.
And they're including that.
But the weakest precondition, that function, is just giving you the things that we know have to be true. So anything which agrees with the weakest precondition might be the condition that you start with, and that would be okay. It's just showing you the things that have to be true in order for R to be reached by running the program S. Flip side is also worth pointing out, is that some condition which is even weaker in a sense, something for which not everything from the weakest precondition is true, you are missing a part of the weakest precondition, then you won't get to R. So it's worth noting that if there was some piece of that weakest precondition, some piece of this, again, what's coming out, it's just a Boolean statement. It's just a bunch of things which may be true. That's what R is. That's also what Q is, the Q that's coming out of this weakest precondition thing.
Isn't that implied by the term, sorry, isn't that implied by the term weakest precondition that it's not true, then therefore R won't be true?
Exactly.
Okay.
Yeah. And so that's the idea is, if there's something about whatever conditions you started with that aren't true from that weakest precondition, you're not gonna reach R. We know that. Unless some other shit is happening again, like, you know, there may be some other, you know, like someone's going into the memory and typing shit manually. It's like, okay, well now we violated everything. But you got to R independently of the fact that you ran S, if that's the case. Like, in order to get to R because of S, you had to have gotten that weakest precondition. You had to have had everything that was true about that beforehand. So a lot of times, to describe the weakest precondition, we're going to use this programming language that Dijkstra came up with for talking about it. This guarded command language. And unfortunately, the do loop is the one piece that I kind of glossed past. So we'll write it on the board to show you. That's the part that gets weird, and it's not like a normal programming language, but it makes for an interesting approach to this. So we're gonna talk about this programming language. This is not necessarily programming language you actually want to write programs in. It's just a programming language that's easy to wrap your head around. What does the weakest precondition look like? So one of the things you can do in this program, the programming language, is skip. It's just like, if you see this thing, don't do anything. It's like a no-op inside of an assembly language. A lot of languages have a skip. Some languages don't bother with one.
Is it like the underscore in Go?
Well, the underscore is usually used for variables, but yeah, if you would have a circumstance where you can do the underscore. If you have like underscore equals underscore in Go, that would, the compiler's not actually going to do anything.
That kind of takes us back to his question though, because it's not literally, I don't think it's literally the no, it's like making it on top of thing where it goes over.
Yeah. In this case, it would. Yeah, the idea is that it's in this case it would be something that would literally do
It's
nothing.
effectively doing what Constantine said, but not
Yeah,
literally.
yeah.
So far.
It would be like having a continue at the end of a loop or something. Like it literally does nothing. Like inside of Python or something, if you put continue as the second to last line inside of your while loop, well, that's not doing anything. So this is literally doing nothing. And that's the point, is that the weakest precondition here, it's literally doing nothing. Whatever the R was, if you ran skip, well, you had to have already started in R, because skip is literally doing nothing to the state of the system. That's the point. You also have another interesting outlier, abort. Okay, what did you have to run? Well, what state did the program have to be in when you ran abort to get to R? And the answer is false. There's literally no precondition that you could start with and run the program abort and get to R. It doesn't matter what it is. So yeah, in a sense, you're not going to get to a postcondition R. So that's, how practical is this? I don't know, but that's, I think they included this one inside the guarded command language in order to try to get you to think about things like that.
It's kind of an equivocation, isn't it? So you
Yeah.
can't achieve a post state
Yeah.
if you do nothing in between the pre-state and the post state.
There is no way to get to R, and so that's the idea, is it just gives you false. And so in order to get to R, your precondition had to have been a contradiction. And so in a sense, the computer had to already be broken for you to get to R from.
But it's almost a complicated way of saying R and precondition aren't the same thing.
Yeah.
I don't think so, because I think that's what skip is, right?
Yeah, skip is saying that they're the same thing. In this case, what we're kind of implying here is that the computer had to have literally been broken in order for you to get from abort to R.
I mean, I think you're kind of going along like mathematic axioms, where
Yeah.
skip is +0 and abort is times.
No, I think that's what he was just saying, is that skip is almost kind of like a +0. And so you could
Yeah,
have like,
skip
you
is
could
like
have,
plus.
you could have like a series of skips, but that's still not R as well.
Yeah. You're exactly right. So skip is like +0 because that is the
So
identity
you
function.
technically can have +0, but then
Yeah.
+0 would not be
That's all.
R.
And then times 0 inside of a field would be would be a degenerate case. Basically, there's nothing you can do to get you to wherever you want to be.
Yep.
Another thing you can have inside of Dijkstra's guarded command language is sequence. So you can have one program, semicolon, another program. And so what does that mean? Well, okay, the weakest precondition kind of makes sense in this case. It is the weakest precondition of program, semicolon, program to get you to R means that you had to get to R from the second program, and then that was the result of, that's where you get to from the first program. So it's the weakest, what is it you had to have true before you ran S1, such that after you run S1, it makes whatever has to be true to get to R from S2, you know, using S2. Yeah.
But is this basically just the whole thing just trying to like describe like large step semantics backwards?
Yes.
Like
Yes.
you take that and like be like, okay, what's the like easiest, the most least restrictive way I can run this like in reverse?
Exactly.
Okay.
That's exactly what we're doing. Yeah. And so that's part of to what Pants was getting at earlier, is that you know, in a sense, this is one of the paths that gets us into our much more sophisticated understanding of semantic definitions of languages. In a sense, weakest precondition is trying to give us a particular semantic definition of a language. We're choosing a definition of a language, and then it's giving us manipulations to the state. So it's representing the state transitions that way. And so the strongest post condition is usually the way that we would write the semantic definition of the language. But weakest precondition is kind of, you can get from one to the other most of the time. And when you can't, that's another interesting property of a language. So anyways, assignment, that's another interesting one. So X colon equals E, that's the way that they write it down in this guarded command language. And so, okay, what was the weakest precondition that gets you to R if you had X as being assigned to E? Well, E has to have been well defined in that previous condition. So you couldn't, if E isn't well defined, then who knows what the behavior of the program is going to be. So E has to have been well defined. And this is the thing that feels like a cop-out, but like, if X suddenly were to become the same value as E by magic, then we know that R is true. It's like, okay, well that's cheating. It's like, well, okay, but again, we're talking about mathematically deriving this. And so then the idea is, whatever it takes to make this logically true, if we know this is true, we're good to go. This is essentially what's happening here. So yeah, so like, that means if somehow magically the value of the variable X was already E, and then we would know that R is true magically. Maybe there's reason to think it's not already true. But if it suddenly became true by magic, then we reach R, that's enough to know that we were in a state that can get us there. So weird.
Is X not considered to be a variable that's free in R, or?
We're not, so that's, is X free in R?
Is that not a requirement?
R is all encompassing.
Yeah.
And so it's not free in that sense. It's definitely bound. Again, like that's part of where it's a little bit different from like from normally how we think of semantic definitions would be closer to a strongest post condition. In this case, since we're thinking of weakest precondition, X is bound to something, whatever it happens to be bound to in R. And so in the sense, in this context, we are thinking of it more mathematically speaking.
So it's bound by possibilities of things that are R.
What?
So it's, X is bound by, X has to be something, because you said R is all encompassing, so X
Yes.
has to be something within R.
Yes.
So X is bound by the context of what is R, of things that are in R.
Yeah, yeah. It is as bound by R as it is bound by anything. So maybe maybe there is no other thing happening inside of X. Maybe X has no other bearing on the nature of R, in which case then it doesn't matter. But that's kind of the point. Maybe R is implied by everything. R is like tautologically true, in which case then, yeah, okay, we're already done, because this is true if we know R is true anyways.
What kind of a thing is R? Is it a logical value, or is it a logical sentence, or?
Yeah, it is a predicate.
It is a predicate.
It's a predicate in, it's just a predicate describing the state of the combined system.
Yeah.
Yeah.
So it would basically be like the whole memory of the.
Yeah, potentially, yeah. A whole bunch of logical statements about the entire state of memory, something like that, yeah. So now we have conditional statements. Kind of another interesting one here. So if B, for some Boolean statement B, then S1 else S2 phi, so that's just a regular if statement. And so the weakest precondition of this to reach R is if B is true, then the weakest precondition is the weakest precondition of the first part, and if B is not true, then it's the weakest precondition of the second part. So it's like, okay, well that's also not helpful, is that, again, remember, we can start collapsing these things. So if there's some thing about B which we know is intrinsically impossible or something like that, then we can collapse whichever of those branches we're talking about. If there's nothing in B that's intrinsically impossible, then we have to keep both sides for now. And so we continue to work our way back. And so these things get increasingly complex. This weakest precondition gets monstrous if you get to any kind of real program or whatever. And that's where loops, oh boy, oh boy, oh boy. So, okay, all right. So we're gonna have do, okay, say B1 leads to S1 box. This is a Dijkstra's guarded command language. B2 leads to S2 box. You can have any number of boxes. And odd.
Wait, so what does the box mean?
So, Dijkstra's guarded command language. Each one of these things is a condition. If that condition is true, then it's going to execute this thing. Okay? And what ends up happening is the way Dijkstra's definition of guarded command language is, it's non-deterministic. Which of the Boolean statements is true will have its program executed.
So it's like the box is just a bunch of else ifs.
A bunch of else ifs. Yep.
Okay.
So in a sense, you can think of this as a while loop. So if we were to translate this into, like, let's say, a C-like language. I'm not going to restrict myself to just C, but a C-like language. It would be something like while, okay, B1 or B2 or or okay? Do, or odd down here. Okay.
Wait, so is it basically like an or? I'm a little confused, like.
Yeah, so is
Well, it's this while on the outside, and inside of here, if B1.
So if any variation of B equals any variation, that's the true, or?
Then it would be like if B1, then S1, but it's not quite this simple, okay? Else if B2, then S2, ... okay? So it's only gonna do one of these. But here's where the trick comes in, because it's not actually doing that either. What it's doing is it is actually, we're gonna have statements which are true, and this is an empty set.
So.
Okay, and then we're gonna have statements blah 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 plus equals 1, or a B1 or
So all these differentials can append to the
B2, okay,
right.
and they each are one of the things that could happen. And then here at the bottom, random number selection of the statements which are true, okay, and then run, run S sub whatever, whichever one, essentially what's happening here. So we're picking one of the Boolean statements which is true, and then executing its program.
Wait, and what's the connection back to?
So this is the loop. This is the only loop that
we're assuming we formalize this as the while loop already.
That is the loop. So yeah, in Dijkstra's guarded command language, this is the loop.
So on your if, you're saying if we pick any random statement from within that loop, or?
Yeah, so what happens is the behavior of Dijkstra's loop system in his guarded command language is that we randomly select on each loop one of the statements where the guard is true, execute its code, and then reevaluate all of the Boolean statements and randomly select one of those that's true, and then keep doing that until you get to the bottom of the do loop and none of those Boolean statements were true, and then you're done.
Just make sure I have the context here. The idea is that if we're going to apply weakest precondition to loops, we have to formalize them this way first.
You don't have to. This is the language that Dijkstra chose to demonstrate the weakest precondition concept.
So you see, if you run through a doom loop and every statement within that doom loop isn't true, then what's remaining is what you're looking for?
Yeah. So yeah, if you go through here and none of those Boolean statements were true, then we're done with the loop. In a sense, it's kind of like an expanded version of a while loop. Instead of it just being one statement at the top, it's like this hybrid thing where it's a whole bunch of different possible statements, and then we randomly select one of them to execute.
Yeah. And then when you randomly select one, it's not a loop anymore, you're evaluating that one statement.
You're evaluating the one statement, and then once you're done with that statement, then you go back and reevaluate all the things in that loop again.
So what are we looking for as we evaluate each statement individually, whether it's true or not?
Wait, so you evaluate all of them eventually?
No, so all of these Boolean statements, theoretically, we're evaluating all of them each time we go through the loop. And then one of the statements which is true, we execute its S sub whatever.
Yeah, but then you said, and then you go back and evaluate.
And then after you perform S1,
Oh, okay.
now you go and reevaluate them all again. Oh, that S1, B1's not true this time, B3 is true.
And so you continue until they're all false.
They're all false.
Okay.
But you like randomly select out of the ones that are true?
We randomly select out of the ones that are true.
So
And there are no
whatever
side
gets-
effects, so you don't have to worry about like them executing and like making side effects, right?
Oh, they might be side effects,
There's
yeah.
this one has two that are potentials, like, or not.
Evaluation of the booleans, hold on, see, evaluation of the booleans don't have side effects,
Right,
I'll say that.
Yeah.
There presumably will be side effects of the S statements,
Yeah,
if
it's
there
like
aren't,
execute the
then
entire
Yeah,
list.
it's
that's
gonna be.
mutation
Right.
statements,
Yeah.
which is what we're.
Wait, so what is the point of this like being so completely different from like old programming languages? Because like the programming languages, it kind of reminds me like of the while and then the switch loop thing.
That is
whatever, but that's
fair.
so different.
That's fair. I think one of the things I'll point out is what we consider to be normal and not normal definitely came into existence after this description happened.
Oh.
Like this, so Dijkstra wrote that in like 76 or something. Well, it was published in like 76 or 78 or something like that. So C certainly existed, Algol certainly existed, a lot of these languages that we think of today existed. But were those the only ways to do programming? I don't think it was clear at that time that we were all on the same page about that. I mean, there were still, as Dijkstra, I think his go-to considered harmful wasn't written for several years after that. So.
APL was still a top 10 language.
Oh, easily. Yeah. Well, actually, I don't know. It may have been before that. Like it might have been. I don't know, because wasn't APL late 70s as well?
Yeah.
So
I
you
think it was the highest it reached was top 10 somewhere.
Yeah. So it could have been that he wrote this book before that happened, even. So
It's like Fortran era, wouldn't it been?
Yeah, Fortran, Algol, C. Well, it would have been the beginning of C. Yeah. Beginning of C, Fortran, Algol, Pascal would have existed by that point.
Lisp.
Well, yeah, Lisp has been with us since the beginning. Or lambda calculus, as we did last month. Yeah.
What's the purpose of the, I mean, I was with you until run a random statement.
Yeah, exactly. Yeah.
Is that something that we defined in this, or is that more like observational behavior, or why not?
Oh no, that was the definition of his language.
Okay.
And again, I'll point out, this guarded command language that he's describing here is not necessarily a language that you want to write real world programs with. It is just a language that's really interesting for looking at weakest precondition. And in fact, this being this complicated actually makes the weakest precondition a lot more complicated. And I think that's why he picked it the way he did, was because he's trying, when you're thinking about weakest precondition this way, it tries to break you of a bunch of habits that you're probably gonna fall into if you know which statement is gonna run. In a sense, he was trying to steer you towards a way of writing, especially your loop invariants, which we'll get to that in a second. But he was trying to steer the way that you thought about these things with this choice of language. You don't want to write programs in this language, but and this is not something that's required to make weakest precondition work, or even to make it work nice. In fact, this makes it work.
But he's basically saying that by designing with the weakest precondition in mind, you can preclude the lowest number, or you can preclude a lot of bugs.
Yeah, I think he designed this language so that when you learned the weakest precondition with it, you didn't accidentally learn bad habits with the weakest precondition. That's why.
So, is he trying to force you to make only one Boolean be true at once, or make all of the S's have similar enough effects that they're comparable, or both?
He's trying to drive you towards better loop invariants.
I mean, so
Or
one easy
general
way
business.
is like just make each BI, replace it with BI and not every other BI, so
Yes.
that you enforce the order.
Yep.
So it's like, you
That
want
would
to like be like, oh, just make only one Boolean true by brute forcing it.
Yes.
Okay.
You can absolutely do that.
That sounds like an important thing.
Oh.
Wait, so doesn't it make it look non-deterministic? And isn't it like a
That's
bad
right.
thing because
That's
like?
right.
But isn't that a bad thing because like?
Why is that a bad thing? That's one of those things. Weakest precondition can handle that.
Well, but it's a bad thing because it means that like the series of inputs, it doesn't guarantee a series of outputs.
That's right.
But that's a problem.
So
No,
the program that you derive should be invariant,
Yeah.
regardless of what the evaluation order
And I think
is.
the key is
that-
like the term weakest precondition.
Yeah.
That was the point. That again, weakest precondition still works on languages that don't have that weird
Cause he said
non-deterministic
weakest,
behavior.
that's the answer.
Well, it's because he's trying to get you, again, like I said, he's trying to drive you in a direction to not rely on the order
I
for
think
your
the
loop
bigger
invariance.
problem is how do you know what the weakest precondition is?
Ah, okay.
Well, isn't this the formula that allows you to transform WP weakest preconditions? Yep.
No, well, I mean, you're not totally off, but yeah, he picked this weird structure specifically to try to get you to have better habits when you think about your invariance. So here's where the big trick comes in with weakest precondition. These loops, in order to work, we're going to 8:13. Okay, we're okay. These loops, what you're trying to do is you're trying to find some statement that is always true, a loop invariant. And so you hear people talk about loop invariance in other languages and such. A lot of that concept was really what was being pushed here. The concept existed before this, but it was Dijkstra who was really trying to shove this through and be like, this is what makes this approach work. You're trying to think of some logical statement, kind of like your R's, your Q's, all that kind of stuff. Just some statement, the mathematical statement about the state of the system that you want to be true all of the time. And what's interesting is you want, so for your weakest precondition of a loop, essentially your R that you're trying to get to, you want that to be equal to some invariant I and not B1 or B2 or
Correct. I'm about to jump in and try to untangle it by
Yeah.
saying that the idea is there's only one V1, and that makes it easy to prove the weakest precondition of your loop. Or no?
No. I mean, the idea is that somehow knowing that all of these Boolean statements is false at the same time, and knowing the invariant, in fact, we'll make it clear. The idea is that the invariant being true and none of the guards being true implies R is true already. That is what you're doing. And so the trick is you're trying to find I.
Yeah, but what if I don't inherently have an I? What if I is something I don't know until I write? Like,
You won't, and that's the idea. That's the hard part of the weakest precondition, and
Uh-huh.
that's the part that takes some
Okay.
humans fiddling with it.
Okay.
You're gonna have to figure out what I
because if I had
and it's
no
not trivial.
pre-existing literature,
Yeah.
and from a validity perspective, I had a large list of potential variables,
Mhm.
and none of them inherently had to be true, but their being weakest is predicated on some outcome, like being more efficient or something that I'm not aware of, that makes it hard to know what the weakest precondition would be.
Well, in a sense that, for your R, in some logical sense, well, it's really easy to figure out, because instead of making it implies, you could just make it equal. So somehow, if you can find
Okay.
some statement I, where I, excuse me. Sorry, not or, sorry, that was an and. I and not any of these things. If somehow I and not any of these things is actually equal to R and not just implies R,
Okay.
you're done. You've already got your I. Now, in practice, that's probably not what you're doing. You wanna get something that implies R with this, so that it's gonna be stronger than R. And so that all of the art in the weakest precondition is finding this I. And it turns out, in a lot of the correct by construction, a lot of the kinds of analysis that you would do, using formal methods to create programs in some way, almost all of the complexity involves some version of trying to find this I. That's where all the complexity comes. And so you have to figure out, what does that I look like? So let's get to some examples. Some of these are easy. We're gonna take a step back for a second, talk about stuff that's gonna be obvious. Like, you got the program x plus 1. Okay. The post condition is x is greater than 5. What is the weakest precondition that gives x is greater than 5 for the program x equals x plus 1? Anybody want to take it? That's right. X greater than 4. Pretty simple. So another one. So if x is greater than 4 for the assignment, then we know after you do x is x plus 1, then x is greater than 5 after. Okay. So here's another one, conditionals. Okay. Compute the maximum of a and b. The post condition is, r equals the maximum a and b. Okay. So what is that? Okay, so if a is greater than or equal to b, then r is a, else r is b. So the weakest precondition forces you to get to the right setup. Like, it's kind of a silly one. You got that and or thing, remember, for when we did conditional there. Where are we? For conditional. There it was. So if it's literally this. Like if a is greater than b, then it's whatever required that to be true. And so when you implement that down here, it's like if a is greater than b, then
I guess that's how you implement the max, but what does that have to do with deriving a precondition? Because
the precondition in this case for r equals max of a and b. The idea is we are trying to find what s would have to be.
Gotcha.
So then what does s have to be? Well, based off of this, we know that ahead of time, like we know what the weakest precondition would be in this case. Is that like a means, r equals a. So actually, yeah, that is a is greater than b. Implies r equals a.
It's like you're going through the process of implementing the max function, but I don't see what the whole weakest precondition system adds to that, I guess.
Yeah, it's because that one's a particularly simple setup. That's why. Basically, what's happening is this is something that we know ahead of time, and so in this case, we're going the other way around. A lot of times we're talking about like, what did the weakest precondition have to be for that program? In this case, we're doing it the other way around. We know what the weakest precondition is. We know what the post condition is. We don't know what the program is.
Okay. Gotcha.
And so in this case, we found the program S by analyzing a variety of things that we happen to know ahead of time. And that's kind of what they're.
Gotcha.
This is ChatGPT. It's my fault for just taking that one.
I mean, it would have been really useful, like earlier, as we were talking about it, to give that simple example.
Okay, that's fair.
But
This is the big one, the one that everyone points to. Let me get their napkin to erase. Okay. The Euclidean algorithm for greatest common divisor. So let's say that you didn't know that really cool algorithm that gives you the most efficient possible way of calculating the greatest common divisor. You can find it from the weakest precondition. So, in this case, I don't know how well they spell it out here. kind of cheating, but in science programming, they point out a whole bunch of different possible invariants. Again, we were saying finding I is the trick. That's the trick of coming up, of using weakest precondition or doing any kind of correct by construction programming. So in this case, we want to somehow know greatest common divisor of A and B. And so we can talk about a variety of things that we know about the greatest common divisor and see if any of those things help us to get the right answer. And so one of those things, there's a couple things we could say. So, okay, well, what happens if A equals B? What's the greatest common divisor of A and B if they're equal? Anybody know?
I mean, either answer's correct.
Yeah.
Okay.
Yeah. just too difficult. Yeah, that's fine.
Just be a douchebag.
Yeah. So if A equals B, we're already done. Okay, so that gives us a hint.
Or if
Like,
A and B are 1, then it could be 1.
yeah, but that would be enough. Yeah. So if either one of them is 1, then yeah, the answer would be 1 all by itself, just because of the definition. But we'll skip that and we'll say that it has to be at least 2. So okay, that's interesting. But even saying that, oh, we'll skip that one, they have to be 2. Okay, well that sounds like itself another part of the precondition, right?
Yeah.
So they can't be taco. You can't have greatest common divisor of taco and apple. Like, okay, well, can't have that. So you've had to already started imposing things on the types of the data that you put in there. That would be part of the weakest precondition. So, okay, what else do we got? Well, they kind of invariant. We have these intermediate values x and y.
Remember, as you go through the algorithm, the GCD is the same.
That's the weird trick here. Oh, okay. So ChatGPT didn't give you the answer. Okay, interesting. I thought it was gonna cheat and give you the answer. I just realized, no, they just stopped it there. Okay, cool. We can keep going then.
Let's say, boo, this doesn't tell us anything, but.
So, well, there's a bunch of different things that we could look at, but the important one here, the trick. GCD of A and B is equal to the GCD of A minus B and B, which is also GCD of A and B minus A. That is not one that I'm going to immediately explain. I'm just going to tell you it's true. It's a math property, so we're not talking about math properties today and how we find them. This is a thing that I'm telling you is true.
Did you mean to write it like that instead of the second one being B minus A, comma A?
A minus B, B, A, and B minus A. Yeah.
Okay.
That's right. This is true.
Okay.
So, okay, interesting, right? What is this? How does this help us? And it's like, well, as it turns out, if we know if GCD of A and B, if A and B are equal, then we're already done. Return A. If they're not equal, take whichever of these is bigger, A or B. If A is bigger, use this one. If B is bigger, use this one. And then that gives you this implementation. Now I'm going to use Dijkstra's guarded command language for this one. GCD of A and B. Okay? And we'll do this. Do A is greater than B implies A is A minus B. Otherwise, B is greater than A implies B is B minus A. Odd. Return A. Yeah, that's right. You can find this definition using the weakest precondition on guard command language, and that's because, like we said, in this case, the loop invariant they're showing, this x and y, that's because they're treating these values as if they're not, as if they are immutable. So if we switch these to x and y, that's what their particular one is there. So we just say x and y are equal to a and b. Y is greater than x. That would be x is x minus y. That would be y is y minus x. And that's return x. Same thing. It would be just whether or not you treat a and b as immutable or not. In this particular implementation, that is the loop invariant then for this. So what that means is, we pointed out earlier, if it's I and not all of the conditions are true, then we have R. So in that case, R is x equals the GCD of A and B. Okay, how do we get that? Well, as it turns out, let's figure out. So I, we said, is somehow GCD of x and y is equal to the GCD of A and B is invariant. X and y keep changing, but A and B we're keeping the same. Okay? So we've got that statement. That's just, it's an equation, but in this case it's just part of the predicate. And we said that none of these things are true. So it's not the case that x is greater than x is greater than y, or y is greater than x. That's it. So this, not the case that x is greater than y or y is greater than x, means
X is not equal to Y. Sorry.
it means that x is equal to y.
But you said, or.
Yeah. So that means this and x equals y means that, you know, in that case, so we might expand that to be that this statement then would imply that x equals GCD of A and B. So,
Can it find the largest prime number?
can I find the largest
Can
prime?
it find the largest prime number?
So it's not always a prime, it could be a multiple of.
No, this is
multiplication. Okay.
Yeah.
There's the largest prime number.
We're plugging in a couple values in my head, yeah.
Yeah, so,
This will work out.
in a sense, finding this invariant, finding the right invariant is where all the trick comes in. This one was easy. Trace common divisor is an easy invariant to find. But both of these books spend a lot of time walking you through some example problems where you're talking about finding more meaningful invariants or more meaningful problems. But in general, all of the complexity is in finding these loop invariants. The argument has been made that a large portion of programming is itself finding right loop invariants. That we don't always think of it in those terms. But a lot of the trick that you come up with in whatever circumstances when you're doing programming in general is trying to find an invariant. We usually don't have it quite in as clear in terms of this, but that's kind of what's happening.
I feel like finding that weakest precondition is still in any real life application the very, very tricky part.
It can
And the
be,
part
but
that
that's,
keeps-
that is where we are here, real languages and tools. So as it turns out, we do have weakest precondition definitions for some real programming languages, not just this weird Dijkstra garden command language, but real ones. Frema-C has a weakest precondition definition for the C programming language. And so there, in that particular case, you would write your statement, your R, as we kept using the term, in ACSL. So it's this standard notation that you would write. It's kind of like a subset of like Doxygen or JavaDoc or whatever like that. You would write your post condition in a very particular way in C-like syntax. If you're doing something really simple, the WP plugin for Frema-C is going to figure out your program all by itself. If you're doing something rather complicated, you may need to give it some assistance by spelling out for it what the invariant is. But whether you spell out the invariant, you know, or are able to do it with just having the post condition up there, it will then be able to generate C code for you. The C code has no bugs. It will have a proof that the C code works exactly right. So that's kind of cool. And Frema-C's weakest precondition even has some very useful things, some like high-level things that you can use for your invariants. Things like it doesn't have any memory leaks. It's like a thing you can just shove into your R. And you're like, oh yeah, it did all this stuff. And also at no point in the execution did it ever leak memory or like have an out of bounds or anything like that. Frema-C just has that, like, oh yeah, that's a really common thing. Let's just ship that as a library of things you can slap onto the end of your R that just, and then we'll just make sure that we generate your C program that doesn't have any of those problems. And it knows all of the standard library parts that it can go talk to that won't have any problems with that. It knows all the other parts of your code base that it knows whether or not it has those kinds of guarantees already. So it's great. It's not trivial. Again, like you're doing something really complicated, you're still going to have to come up with the invariant because it's going to be like, I don't know. And so you're going to have to guide it with an invariant. You're going to have to like say, here's my post condition, here is my invariant. But if you give it a good enough invariant and a good enough post condition, then it's going to be able to connect the dots and be like, oh, okay, I can generate the C program that does that. So again, it still requires, it's not fully automated, it's still going to require you to go poke around it a little bit. But the C code itself can get spit out, and your C code spit out using that thing is not going to have any bugs, not in the traditional sense. I mean, it doesn't save you from a broken compiler, like, okay, well, it doesn't save you from someone took a hammer to the computer that the code's running on, like, okay, well, nothing you can do about that. But like your code didn't introduce any of the problems. Daphne, a language that they're using a lot at Amazon, for example. There's other places they use it as well. Daphne is the language that they wrote the replacement for the IAM resolver. So the system that checks to see that your permissions are working right, that has been replaced with Daphne, and is now the most run Daphne code ever. I think they said it's something on the order of like quadrillions of times a day that it runs. It is an amazing number of times. So like every AWS API call, dozens of times that program runs. Every single person who runs every single AWS API call, every single time, it runs that Daphne program dozens of times. They have not found one bug yet. And it's because they wrote the thing in Daphne with Y3 using weakest precondition. Isabel, Rock, Lean, they all have definitions of weakest precondition, and you can use them. As we were talking about semantic definitions of a particular programming language, you could, depending on how you define your semantic definition, you can use that to turn it into weakest precondition, or weakest precondition is in some sense effectively the same thing. And so if you're doing like programming language design kinds of things, it will definitely come up as well. So yeah, why would you use something like this? You know, there are circumstances when you would use program derivation. If you're, you know, doing something with like the avionics software, and it's like a really important critical part of the system. Or if you're like doing the like check inside of the credit card chip, like you don't want to have a bug in there. And so if you spend the time to do it right, use the language that you've got a weakest precondition for, you've got your invariants written out, you've got the whole thing going, you're not going to have any of those kinds of bugs. It's not going to save you from something you didn't think to check. You know, it doesn't, like with cryptography or whatever, it's like you can check to see that your cryptography matches all kinds of things that you think to check, but it's not going to save you from the thing you didn't bother to formalize and say. You know, it turns out like, oh, my program has a problem if you know, A and B are, you know, if one of them is divisible by 4 while the other one is divisible by 7. It's like, okay, that wasn't some shit that we thought to check. Like, if it turns out your computer breaks when this bizarre combination of things happens, well, nothing about the way that we did this algorithm guarantees that won't happen. You would have to put that in there. Now, probably you could find a different algorithm that would solve that problem, but like, it's not gonna save you from shit you didn't think to ask for. But if you are able to specify exactly what it is, the behavior you're looking for, you should be able to get this stuff, and it's largely mechanizable. So if you can describe your problem with enough specificity to say this is exactly the kind of behavior we're looking for, you're going to be able to make it work.
Can you ever get contradictory code if you have multiple different weakest preconditions?
Yeah, if you have different definitions of the weakest precondition, yeah.
So if you have several things that are weakest preconditions and you try to generate, can you do like code that answers to all of those weakest preconditions, or does it only work if you have one singular one?
So, okay, it depends on what you're saying. Are you saying different definitions of the function, the weakest precondition function, or are you saying different outputs, different things that came from the weakest precondition?
So I'm saying if you have several things, if you don't have a singular weakest precondition, so you have a bunch of things that must always be true. You say in practical usage, basically things that can never fail. But if you have multiple fronts on which the thing can't fail,
well, no, so there will only be one weakest precondition.
Okay.
Now, it could be that you've got a different definition of the weakest precondition function, but any one implementation of the weakest precondition is only going to give you one thing. It could be a whole bunch of ors, it'd be really complicated, but there's only one in that sense. And so 2 different like programming languages that you tried, like maybe they would result in different behaviors or something like that. That's possible, but you're, again, like either there was a flaw in how the thing was written or something like that. Like,
but what if it's not an or? What if it's an and? What if I have something, it must be true, and I have another thing, it must be true?
It's a full Boolean expression.
Yeah, it's
okay, that's, okay, yeah.
Yeah, you still have to satisfy.
Okay.
Yeah. So whether it's an and or an or.
The weakest precondition is long of a condition that I want it to be.
Yeah.
Yeah.
This is true, or this is true, or this is true.
Yeah, you could have a whole bunch of ors in there, and then any one of those could be true, and then that would be sufficient. Yeah. So the downsides of the weakest precondition is, like, it turns out, you know, this knowing your program works is hard. It's harder than just writing a program and hoping it works. And so that it's expensive. It requires specialized knowledge to be able to do this kind of stuff. You know, it's nice, it's proof, you know, driven, it's elegant, systematic, you can mechanize it, but the downside is, you know, it's not easy to do this shit. Coming up with these loop invariants requires a clever person who is trained on advanced computer science and mathematics concepts. It's not going to be as cheap as, you know, like an intern slapping stuff into ChatGPT. ChatGPT is probably not going to be very useful at coming up with these loop invariants, to be honest. Like, it's not the kind of thing it's going to be very good at. large scale systems, the complexity goes up so high. I mean, again, if you're talking about something like SEL4, well, it's only been done once, like, you know, so it's not infinitely expensive, but it is definitely more expensive than doing just, gee, I hope it works programming. It's definitely not fully push button, you know. Coming up with the proof is, now that's one of the nice sides is if you come up with your proof, like with the pharmacy thing, you come up with this full ACSL spec, ACSL spec, and you have your post condition specified, you have a really good loop invariant, then it'll generate your C code, and if something happens, like the compiler gets updated, or they know more things about a better, more efficient algorithm, well, you know, they'll go and rewrite the C code for you, and you get all the advantages of that stuff. But then it turns out that writing ACSL is harder than writing the C program in the first place, generally speaking. So it comes with some downsides. So closing thoughts here: weakest preconditions. It's a design methodology, not just an after the fact proof system. So that's one of the alternatives that people did in the early days. I mean, they still do it, is taking an existing program and trying to prove that it is correct. It turns out that is an even more expensive thing to do. I mean, as expensive as this is like coming up with your proof at the beginning and then extracting the program from it. It's even more expensive to take an existing program and then prove that it is correct. There are still reasons why you have no other choice, and so we'll still do that. Generally speaking, most people in the formal methods world would probably say it makes more sense to use correct by construction, program synthesis, whatever, what have you, than to try to do it, to take an existing program and prove it correct. So SEL4 is a good example of that. Like, they made proofs in Isabelle, and then they got a large collection of things that are trying to extract the proof from the program from the proof. So they're largely not using weakest precondition. They are in some cases, but not always. This is an example of correct by construction. That's not just the weakest precondition predicate transformer. They're doing a bunch of things. But it is correct by construction. They have this huge mathematical proof. From that, they're generating the C code. And it's, as opposed to, for example, there is an effort going on to try to prove parts of the Rust compiler correct. Unfortunately, right now, they're taking the other approach. They're because Rust is not as, like, it feels like it's way more better defined than a lot of other programming languages, but it's not defined like at a full semantic definition level. We don't have that level of knowledge of Rust yet. We're working on it. Like, there are people working on that. And so it will probably be one of the languages that from its inception to the point where we have a full formal spec, it will probably be one of the shortest that has ever happened with. But today we don't have one that everyone agrees on. Right? It doesn't exist yet. And so that means that we don't have, you know, like, program extraction in the same sense with the same level of confidence with Rust that we do with C, ironically. Now, in fairness, it's like a subset of C, and it's not exactly trivial, but the irony is that there is a small set of C code which, for the given level of effort, is easier to make more secure than Rust. But it's, again, a weird edge case. Right now, there are people working on making a proof of the correctness of parts of Rust, and they are taking the other approach. Eventually, we're going to have a definition clear enough that we can do, like, weakest precondition for Rust. That's going to be great when we get there. But it takes a long time to come up with a spec that is that level of clarity that we can take action on. In a sense, we're trying to, with this approach, the correctness by construction thing, is you're creating your proof, which is harder than programming, but from that you get the program. So that's nice. And the idea is, you know, it would be interesting to try it if you're curious, if you've got some really complicated, especially like a math-related thing. Give it a shot. Find a language that you've got a weakest precondition definition for. Try to specify your problem with a level of clarity that you can actually get one of these tools to extract the code. You know, it's not going to be, you're probably not going to write some big, you know, Java-based like, database-driven thing from scratch using weakest precondition in a meaningful amount of time. But if you had some very complicated, like numerical algorithm or something, you probably could. So, any other questions?
Bravo.
Yeah, thanks. So for follow-up, like I say, this is the Dijkstra book. It is legendary, it is important, it is not easy to read. Yeah. This was a book that I read that got me inspired on all of this stuff. Science of Programming by David Greaves. It's cool. I liked it. It is as I mentioned early on, like the symbols and stuff are frustrating. I don't know that this is necessarily the book that I would recommend, even though it has a special place for me. I think this one is a much more reasonable choice. Some of the examples in this book are much more relevant and recent. Like this one has a really cool section where they're performing program inverses because he was a math nerd and he liked the idea of like algebraic inverses of the behavior of a particular program. And this is something that weakest precondition can get you to do as a party trick. It's not like actually useful most of the time, but like, okay, cool. This one has examples which are going to be much more practical, that are going to be meaningful. And if you crack it open and you look, you will notice that they're using like, you know, math symbols that came out of LaTeX or Tech or whatever. And like it's dense, and so, you know, there's going to be parts of this that are going to be like, what's going on? But yeah, and it looks like, I mean, it's been a while since I've thumbed through this one. I think they are using, they're using Dijkstra's garden command language here as well. And so the same thing. Oh, okay, yeah, a thing I forgot. That do loop thing with the boxes, that's also the behavior of the if. So the if is doing the randomized. I forgot about that. So, and once we got through the weirdness of how it works with the do, like, I think understanding how it's the same thing in if kind of makes sense. So. Yeah. Any other questions or anything?
We talked about some of the rules earlier. Was it making the comparison to like mathematic axioms with like identity and such? Do the other mathematic axioms make their way into rules with like inverses and like syllogism? I think that word is.
Yep. So yes, and that is an interesting area that maybe I should send you down the programming languages path, because it sounds like you've got a lot of, you will have fun in that area. You are asking the right kinds of questions that are way outside of the scope of just this. But yes, you are absolutely right. Like that is an area of very active research in programming language design.
Okay.
Of like trying to find languages that look like a lot of those kinds of concepts. Yep. Absolutely.
So like some of the problems with mathematic axioms are like the weird undefined things like dividing by zero. What does dividing by zero look like in this? Or is that not a good metaphor?
Well, the closest thing to dividing by zero in this would have been that abort.
Okay.
Yeah. So it wouldn't be quite the same thing, oh, we are
It was a housekeeping issue, yes, we didn't.
yeah, we are running later on time than I realized, yeah, okay.
Don't worry about it.
Still not 9, it's still
You're on
9.
You're on the Zula food.
Yeah.
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 Is this also informed the prologue design? I know it's like it runs differently, but some of it feels vaguely similar, like inverting programs. Like I was like, oh, prologue, right?
Oh, yeah, I mean, some of this stuff was definitely contemporary with that. I think that the, inverting programs was, I think, that was more of like a Greece thing than a Dijkstra thing per se, I feel like, but yes,
Good,
like,
man.
that was,
We got to,
certainly,
get our new
when they were designing
salesperson,
prologue, we could.
we gotta get our new salesperson,
Like prologue came.
working on those phone calls, got a script, he's
Like,
going.
because
Oh.
that was the 90s or something like that.
I don't know, and trying to truck on
Fixing
some
it up.
million.
Well, yeah, but it was developed, it was like under development for a while.
Yeah.
Saves me shit, I've been drinking too much caffeine, drinking too much alcohol, but we gotta get done with this next 6 months or so. And I'll live,
Thank you, Charlie. Yep,
probably.
But I think like the Golang book, it was also written in Trough, right? But like it doesn't, it has to be more modern now, or like how does that work?
Yeah, well, I mean, again, I mean, he definitely would have had better font support by that point.
Right.
So that, it was written in a very different era.
Right.
Yeah, when you were talking, I went and looked up the difference between trough and Roth and Groff and all that.
But you know, like the Go Programming Language book, it was written like within the last 10 years, right? So it was actually written in Roth. The guy, he wrote it in Roth, and it's written that it was written in Roth, so.
Well, Roth originally, like for line printers, it didn't have fonts.
Right.
Trough was the one that added fonts, and then,
Oh.
but then I think Inroth was like next gen Roth.
Okay.
I think that came even after that.
And then
And
there was
then the
also
GNU
Groff, right?
people had to put a G on it,
I don't think they have the little things here.
and, yeah.
Oh, they actually have
The Roth was an abbreviation for runoff.
Are you
The
letting
phrase
Go
to print something to run off the document.
Oh, I didn't know that.
I work in healthcare, we still have that.
Yeah.
We still have the old
Towels here as well.
Fortran.
Yeah,
I'm just
yeah.
waiting for the day when I run into a punch card computer at a healthcare institution.
Look, they keep finding legacy systems that are.
Yeah, they fucking can't catch up to the 1980s.
Oh, if anybody needs parking passes.
Have you ever seen what the big EMR systems look like? It's like a blast from the past from a software design perspective. You're like, oh my god, fucking bring back 95. Why did you just fucking wear tie-dye while you're at it? It's fucking awful. I don't know how they fucking spend their money on that shit. And people go, oh, why is it so expensive? And it's like,
Thanks, Charlie.
Thank you.
fucking awful. I don't know how the fuck I guess they didn't because everyone complained about it all the time. I was like, how the fuck they hung on this long? I like to make a joke that healthcare is the only industry where regulation creates more innovation. They fucking spin their wheels and whatever they can get away with, but the government kicks them and they'll stop doing that.
Yeah.
Yeah.
The one where they push them on the electronic health records or maybe the pharmacy one where they may just have to electronically send stuff to the pharmacy or.
Oh, they still have to do that all over. Yeah, it's not just pharmacies. They all still fucking do that shit. That's fucking crazy. They still use fax machines.
Yeah, I know.
For
They-
like
they
period.
treat it as a secure
They're
method of-
famously the what like. They're famously the people who keep the fax
Alright, how
machine
much pizza we have
companies
left?
The thing that I hate is that they make you,
You taking the pizza constitution?
I can take the cheese one.
I'll take some of the cheese.
I'll take the cheese. Can I take the cheese? Do you wanna take this one?
I'll take some of the veggie and how much? I'll take the veggie and like a couple slices.
That's good. Alright, I'm gonna take off. I'll see you, Charlie.
Yeah, see you.
It's really good talk.
Yeah, thanks.
But yeah, they're famously.
Every time I,
and
We do this, I like blow $100 a book.
Fucking fax machine.
Oh, yeah. Sorry, and you're welcome.
Exactly.
Yeah.
I'm not complaining.
Yeah.
You wanna take any?
Nah, that's all right.
Thank you for sponsoring it again.
Absolutely. Well, one of these days we'll get someone else to sponsor.
Look at it. What is the number?
Anything else I can carry out?
You got your parking pass?
Yeah. Okay, these are yours, or, I'm just gonna help carry part of the way if you need.
Yeah. Well, unfortunately, we didn't get the drinks, but that's all right. I think we're okay.
I didn't realize they had that water machine out there.
Yeah. I wish I'd come up with some way that I liked explaining the do stuff, but I was realizing like, oh, that was exploding really quickly. No,
It was a good enough overview, you don't have to get everything.
No, I mean in the
You
LaTeX.
had the slide up there which said like the while loop gets complicated, and then
Mhm.
like we spent 35 minutes talking or whatever.
Mhm.
And I was gonna like be all snarky at the end of it as we got out of that, and raise my hand and say, well, what was the
Get the
complicated part?
Oh, no, let's put it on, because they're about to number.
But yeah.
Yeah, so what was the complicated part?
It's funny because these specific kind of nerds smell very distinctly. Not good.